All right, so in chapter 3, we had 3 different approaches for solving equations: rewriting, undoing, and looking inside. We can also use those same strategies for solving inequalities. While the one variable inequalities you solve today look different than the ones at the beginning of the chapter, the basic process for solving them is similar. As you solve equations and inequalities in today's lesson, ask yourself these questions. How can we represent it, and what connections can we make, especially to things we've already done? Review what you've learned at the beginning of this chapter to solve the inequality. So if we're going to solve 2x plus 7 is less than 12, we would subtract 7 from both sides. 2x is less than 5, and then we would divide both sides by 2, leaving us with x is less than 2.5, 2.5, or you could leave it as 5 halves. So in order to graph that on a number line, we're going to want to put 2.5, which is going to be the number that gets the circle around it, sort of in the middle. So we might put 2 here and 3 here and let a line in between represent a half. So every other line would get labeled, and that still gives us a minimum of 5 numbers labeled on the number line. So an open circle on 2.5 and less than, we would point towards the lower side on the left. Now, if we want to, we can check for solutions. First, it says, what is the boundary point? Well, the boundary point is 2.5. That is the number that we put our circle around. Is it part of the solution? Because it was less than, we drew an open circle, which meant that no, the 2.5 is not part of the solution. Less than does not include the 2.5. In general, how do you determine a boundary point? Well, really, you're solving an equation, right? You solve it as if it had an equal sign, and that gives you your cutoff point, your boundary point. How do you determine the solutions of an inequality after you've solved it? Well, one option is to graph based on the inequality symbol that's there, the less than symbol, but you can also test a point on either side of the boundary point. So for example, we think the solution is to the left. We could plug in 1 and do 2 times 1 plus 7 and see if that comes out less than 12. Is 2 plus 7 less than 12? Sure is. Because that came out to be a true statement and it was in the part that we thought was the solution, we must have drawn our arrow facing the right direction. Now, absolute value is the numerical value of a number without its sign. Positive values only, because we're considering it to be like a distance, right? Absolute value can represent the distance on a number line between a number and 0. Using the looking inside strategy for solving equations from chapter 3, solve 3x minus 5 equals 16. So what we need to do is say, well, 3x minus 5, because it's inside the absolute value bars, it could equal 16. The absolute value of 16 would give us 16. So we would add 5 to both sides. We'd get 3x equals 21, and we divide both sides by 3, x equals 7. So 7 is a possible solution. But what's inside the absolute value bars might also be equal to negative 16. If this was worth negative 16, when I took the absolute value, the distance from 0, I would get 16 as a result. So I'm going to add 5 to both sides. I'm going to get 3x equals negative 11 and divide both sides by 3 and get a second solution of x equals negative 11 thirds. So x can be 7 or negative 11 thirds. And both of those numbers result in a true statement, okay? Henry is riding his bike along a straight road when he gets a call from his mom asking where he is. Henry says he's 7 miles from home. The number line below with the integers from negative 10 to 10 represents the road Henry is traveling along. Place Henry's home at 0. Okay, we can do that. Then mark the positions on the road on the number line where Henry could be when his mom called. Well, if he's 7 miles from home, he could be up here at positive 7, or he could be over here at negative 7. And we don't know which one, because along the road, both of those, because they are distances, are 7 miles away from home. Use absolute value to write an equation giving Henry's possible location. So what we're saying is the value could be positive 7 or negative 7. So the absolute value of, and we've got to pick a letter, so let's pick H. H equals Henry's location. absolute value of h has to be 7. So I could put a 7 in here and take the absolute value and get 7. Or I could put a negative 7 in here, take the absolute value and get 7. Those are both possible locations for Henry. Henry continues along his route when his friend Emerson calls, asking where he is. Henry says, I'm 3 miles east of my house. Great, says Emerson. I'm just 2 miles away from you. I'll see you soon. And hangs up. Okay, draw a new number line, marking Henry's position and Emerson's positions. Well, Henry says, I am 3 miles east of my house. Now, we know that we had Henry's house at 0. If he's 3 miles east, that puts Henry right here. But Emerson is 2 miles away. So Emerson might be here at +1, and Emerson might be here at +5. And we don't know which one. So how do we go about writing an equation? So we're going to talk about some really important things here. So first of all, we're going to say the difference between Emerson and Henry's location is 2. Now, we know Henry's location is here at +3. That is a constant. So if we take Emerson's location minus Henry's 3, we've always got to come up with a difference of 2, right? Because the difference between 5 and 3 is 2. The difference between 1 and 3 is 2. So we might also have come up with 3 minus e equals 2, because the 3 minus e is the absolute value. Regardless of which order I subtract them, when I take the absolute value, it comes out to 2. All right. Now, how did I get these numbers? The number here that you're subtracting, the -3, that's your center point. That is your, I know this number to be true. The e is the thing that we don't know. We don't know Emerson's location. And the 2 is the distance from that center point out to either of the unknowns. Solve your equation algebraically. So if we solved, just say we solved the first one, e minus 3 could equal 2. E minus 3 could also equal -2, because the look inside method says whatever's inside those absolute value bars could be worth 2 or could be worth -2. So if I add 3 to both sides, Emerson could be at 5. And if I add 3 to both sides, Emerson could be at 1. Now, the same thing will work, just for argument's sake, if I had solved 3 minus e equals 2 and 3 minus e equals -2. I would have subtracted the 3 from both sides. Negative e equals -1. So positive e equals +1. Well, we got that answer the first time. And if I subtracted 3 from both sides, negative e equals -5. And positive e equals +5. So I will actually get the same answer, just to prove a point, regardless of which order you put the subtraction in, either the first one or the second one, because absolute value makes everything come out positive anyway. 9-28. Amanda messaged Henry with the following message. I am still more than 5 miles away. Henry is not sure if Amanda knows that he's not at home. If Amanda thinks Henry's at home, draw a number line and highlight Amanda's possible positions. Okay, so let's just say Amanda thinks Henry is at home. So we would put Henry at 0, and we would say Amanda is more than 5 miles away. So she's not at 5, but more than 5. On the other side, she's not at -5, but she's more than that away. So we're saying she's somewhere on either side of Henry by 5, but more than that. And that's why we did the open circles. So Amanda, and we've got to do absolute value. A is going to be Amanda's location. Absolute value of it has to be greater than 5. Well, maybe Amanda talked to Emerson and knew that Henry was 3 miles east of home. So what if she knew that Henry was here at 3? Okay, so we've got Henry's location at 3. That's your new center point. Okay, that's the point that we know to be true according to, Amanda chatted with Emerson and they both know that he's at 3. If she is more than 5 miles away, 1, 2, 3, 4, 5, she could be further than 8. And on the other side, 1, 2, 3, 4, 5, further than -2. So again, if we think about the top one, we have the unknown, which is Amanda's location, minus our center, the thing that is known. In this case, it's 3. And we know that she's more than 5, greater than 5 away. Now, we also could have done 3 minus a is greater than 5, and that would have worked in the other order as well. Now, if we solve the inequalities, do our algebraic solutions match our number line? So let's take a look. If we do a minus 3 has to equal 5, plus 3, we get a equals 8. So if I had done a minus 3 is greater than 5, plus 3, a is greater than 8. Okay, well, that's good, right? That's up here on the right. Well, the other one would be a minus 3 has to be, now here's the catch. We want to do the opposite, right? Before we were doing like 5 and negative 5. And so what I'm going to try to do is say, well, what if I just make it a negative 5 and I do plus 3 is a greater than negative 2? And we would say, no, that's not what we get. Like we said that it had to be less than negative 2. So it didn't work to just switch that 5 to a negative 5. We actually have to say, if we are doing an inequality, a minus 3, it was greater than 5. This time, when we want to switch it to negative 5, we also have to switch the inequality symbol with it in order to come out with a true statement that a is less than negative 2. So the key here is when I go to solve an inequality that involves absolute value, the first one, you just write it down practically the way it is. A minus 3 is less than 5. But when you want the second answer, you have to switch the less than, the greater than to a less than, and the 5 to a negative 5. So it was greater than 5. Now it's less than negative 5. And I know we're going to have to do more than one of this in class, and that's absolutely fine. I fully predict that I will be doing several of these examples live as well. All right. Henry stopped 3 miles east of his house and knows that by now Emerson must be less than 2 miles away. Write and solve an absolute value inequality for Emerson's possible positions. Graph your solutions on the number line. Do they make sense? Okay. Henry is stopped 3 miles east of his house. There is our center. There is our known value, 3. By now, Emerson must be less than 2 miles away. Okay. So Emerson could be at less than 5, 2 miles away. Emerson could be at less than 1. So I'm somewhere between the 1 and the 5, but it's that whole range between the 1 and the 5. But since it said less than, I'm not including the 1 and I'm not including the 5. I'm going to try to write this inequality first. E is our value for Emerson. Emerson is the unknown. I'm going to subtract or find the difference with 3, which is our known value, Henry. And it says less than 2 miles away. So I need to solve this twice. I need to solve, does E minus 3 is less than 2? That gives us that E is less than 5. Great, that's the right side of the diagram we drew. Now, when I go to do the other side, remember E minus 3, instead of less than 2, I need to flip that to greater and make the 2 its opposite, which is negative 2. So when I add 3 and add 3, I get that the other possible location for Emerson is greater than positive 1, which is what we had over here. Now, when you're finished with this, you would actually just connect these. You wouldn't have any arrows at all because you'd be saying all values between 1 and 5. So the other way to say that is that Emerson could be less than 5. Emerson could also be greater than 1. Emerson could be anywhere between 1 and 5. And all I did was combine our two solutions from solving the inequality using the look inside method and making sure that the first one is less than 2, the second one is greater than negative 2. I have to remember to switch both. Now that you've practiced writing and solving equations and inequalities with absolute value, use your knowledge from the beginning of this chapter to consider the inequality x minus 2, absolute value, is less than 3. Can you use the process from problem 924? We're going to say no. It's going to have 2 boundary points because of the absolute value. Solve the inequality and represent your solution algebraically and on a number line. So I'm going to solve it the first time where it looks practically the same, right? I'm looking at this one up here. The x minus 2 is less than 3. And we're going to say x minus 2 is less than 3. Great, we have to solve that one. But we also have to solve, is x minus 2 greater than negative 3, where we flip the sign and switch it to its opposite answer. So if I add 2 on the left, add 2 on the right, x is less than 5. And if I add 2 on the left, add 2 on the right, x is greater than negative 1. So negative 1 would get an open circle. Positive 5 would get an open circle. And x is less than negative 5, so I'm coming this way. X is greater than negative 1, so I'm going this way. So I'm really shading everything in between. So it's the interval, negative 1 is less than x is less than 5. Open circles means none of the equal signs, and I'm saying any numbers between negative 1 and 5. Now, if you want to check this, all you have to do is pick some point that's in between them. Say 1. And I can say, is the absolute value of 1 minus 2 less than 3? Is the absolute value of negative 1 coming out to less than 3? Yeah, the absolute value of negative 1 is 1, which is in fact less than 3. So that random point that I picked does fall in between the two numbers. And if you're someone like me, you're probably going to do it again. You're probably going to check another number like 4 and say, is the absolute value of 4 minus 2 less than 3? Is the absolute value of 2 less than 3? Yay, 2 is less than 3. So 2 different numbers that I picked inside that interval work. So how was solving it different from solving an inequality without absolute value? Well, after you find the boundary points, you have to test a point that's in that possible solution region between two cutoffs. So that would be one thing that's different is, let's see, after finding 2 boundary points, you must test a point in the possible solution region. So you have to make sure you're taking both that sort of lower cutoff and upper cutoff into account. All right, so we've got some really interesting special cases that pop up sometimes. We're going to do 4 total examples here and see if we get anything kind of quirky. So the first one says x plus 2 is greater than 1. So we're looking for values that are greater than something. That usually means that our arrows are pointing out or away from each other because we want bigger differences. So I'm going to solve x plus 2 is greater than 1. I'm also going to solve x plus 2 is less than negative 1. So if I subtract 2 on both sides, x is greater than negative 1. If I subtract 2 on both sides, x is less than negative 3. So my cutoffs are negative 1 and negative 3. I kind of want to think about where I put them so that I can have numbers on either side. We kind of want our circled numbers to be centered. So the negative 1 gets an open circle. The negative 3 gets an open circle. X is greater than negative 1, which means I'm pointing up. X is less than negative 3, which means I'm pointing down. And I got exactly what I expected. My arrows are pointing away from each other, or they're pointing out. And that's because I wanted greater than a number. I wanted my difference to be bigger. See how your center is here at negative 2? I'm 1 away, but more. I'm 1 away, but more. So that's your greater than 1. The second one does not have an absolute value. Don't just start jumping on everything has to be solved like absolute value problems. So I'm going to add x to both sides. I'm going to add 4 to both sides. So I get rid of all the x terms to the right, 10x. Less than or equal to, I get all of the non-x terms, the constants on the right. And when I divide by 10, I get x is less than or equal to 1. And you're like, okay, somehow that seems too easy. No, it's just not an absolute value question. So if I put 1 in the middle, don't overthink it, guys. And I do less than or equal to, which means I have a closed circle, and less than pointing to the left toward the lower numbers. Now I'm back at an absolute value question. You cannot start splitting things up until you have things sort of in the simplest form possible. So I would want to do 2x minus 2, which is in the absolute value, greater than or equal to 0. And now I would split it up. 2x minus 2 greater than or equal to 0. And I also want 2x minus 2 to be less than or equal to 0 because there's no such thing as negative 0. Some of you might see where this is going. If I add 2 to both sides, I'm going to get that x is greater than or equal to 1. You're like, okay, that's reasonable. If I add 2 to both sides, I'm going to get 2x is less than or equal to 2, divide both sides by 2. X also has to be less than or equal to 1. So you're like, okay, what's that going to look like? All of the numbers have to be greater than or equal to 1 and less than or equal to 1. So if I were to put 1 right in the middle, it would have a closed circle, and I would have an arrow to the right. I'd have a closed circle with an arrow to the left. This is actually an all real numbers solution. And I actually could have told you from the very beginning it was going to turn out to be all real numbers, because this says I want the difference to be less than, greater than or equal to 0. Meaning I'm perfectly happy if your number is 0 away from mine, but it could be greater than. Oh, and by the way, it's an absolute value. So it could be -2 and it would still come out greater than, because I would switch to a positive. And all positive numbers are greater than or equal to 0. So there are some quirky, weird ones that you're going to be like, hey, this is all the numbers. And if you put a 1 here and you put a closed circle and then you draw your arrow up to the right and then you draw your arrow over to the left, and that's the point at which you go, hey, it's all real numbers. That's fine. There's nothing wrong with your graph looking like that, because you've still included all of the numbers. You don't have any open circles anywhere, and you don't have any parts of the number line that are uncovered. You do, however, need to remember to finish your question by saying all real numbers solution. Last but not least, if I split this, 3x minus 11 is less than -2, and then the other one, 3x minus 11, is greater than +2. Some of you are going to notice right away that there is a problem. If I add 11 to both sides, 3x has to be less than 9. You divide by 3, x is less than 3. Over here, add 11, 3x is greater than 13, divide by 3, x is greater than, well, 13/3. X cannot be less than 3 and also greater than 13/3. It's not going to work, and I'm going to tell you why, and it should have been noticed way back up here. The absolute value of a number cannot be less than -2. So if you go through all of this work and you tell me that this is your answer, I'm going to mark it wrong, because way back up here, before you did any work at all, you should have picked out and said, this is not possible. It is not possible to have the absolute value of anything less than or equal to a negative. So none of this work should have been done. And you should have done literally no algebra at all. And you should have said, it is not possible for an absolute value to be less than 0. So what is your actual solution? Your actual solution is no solution. There is no solution. So you can put your 1, 2, 3, 4, 0, -1, -2 and leave it empty. But literally none of that algebra should have been done because of the original problem. And if you go through this whole process and you're like, x is less than 3, x is greater than 13/3, like, it does not work, because you cannot get the absolute value of a number less than a negative.